This lesson is on solving linear trigonometric equations. An equation that involves one or more trig ratios of a variable is a trigonometric equation. So these are trig equations. These are not, this doesn't have an unknown for your angle. And same with this one, pi is a number, it's a constant. So those are not trig equations. These are trig equations. We're going to solve these two equations in this domain. Meaning we don't need to find answers that are outside of this domain, although they do exist. Solve for x in the domain 4 sine x cos x minus 1. But the problem with trig, just like any kind of equation, let's say I had the equation 2x plus 3y equals 1. I can't solve that because I have two variables. I have an x and a y. So I need them both to be x's or both to be y's, then I could solve that one. So I have the same problem over here. I've got a sine function and a cos function. So what you need to do is look at your list of all of the equivalent trig ratios, all the proofs, all the little identities, and find something that will allow us to turn two into one ratio. So take a look at what you've got and see if there's any way to take that part that I circled and replace it with something else. Hopefully you found this one here. So I'm going to look at this piece and try to swap it out with this. But one is a 4 sine x and one is a 2 sine x cos x. And we already talked about this before, this kind of question. So the first thing I'm going to do is, instead of writing 4, I'm going to put a 2 in front, and then in the bracket, so basically I'm taking this side, multiplying it by 2, and this side and multiplying it by 2. That gives me the 4. Inside the bracket, I'm going to put sine, well, let me write it all out. I'm going to put 2, I'll put it in red here. So all I've done is kind of factor out a 2 so that I can make these match. So my next step now is I can substitute in, I can swap out this piece here. I'm going to replace that with sine 2x. This is equal to this, so I'm just switching this piece out here. Minus 1 equals 0. I'm going to move this, well, simplify this a bit. This is 2 sine 2x equals 1. I bring the 1 over, divide both sides by 2. Sine 2x equals 1/2. Now this 2x, let me just kind of circle it here. This 2x right here, I can't just say I'm going to divide both sides by 2 to get rid of that. That's a double angle, right? We used a double angle formula there. This strategy I've shown you before is I'm going to replace that. I'm going to say let 2x equal something else. I'll put a theta in there. That way I don't have to worry about the double angle right now. I'm going to change this to sine theta equals 1/2. Now we can solve that. We have a triangle for that. So remember that sine is opposite over hypotenuse. It's also the same as y over r. So I'm going to draw a little sketch here of a right angle triangle. Here's theta down here in the corner. I need the opposite to be a 1. I need the hypotenuse to be a 2. What would that make theta? So this remaining side is a √3. So what would that make theta? Well, if we were in degrees, we would say 30 degrees, but look up at the question, we have to use radians. So my theta in this case is going to be pi over 3. So I've got, sorry, pi over 6. So theta equals pi over 6. Again, looking at our domain, we've got the domain of 0 to 2 pi. So there's going to be more than one answer. Let's look at the Cartesian plane. The first one I found is right here. That's my pi over 6 right there. And we're looking for where sine is equal to 1/2. So we consider the cast rule. Sine is, of course, positive in this quadrant. Sine is also positive in this quadrant. So I pick up my pi over 6 angle. I put it in the second quadrant. There's pi over 6 again. But what I need is this rotation to that terminal arm. And that rotation is going to be 5 pi over 6. If it went all the way to the line, it would be pi, which is the same as 6 pi over 6. But I'm 1 short of that, so I'm 5 pi over 6. So I've got another answer. So my theta 1, the first answer I got was pi over 6. I have another answer. Theta 2 is 5 pi over 6. But remember we did this up here? Theta is actually 2x. So I'm going to switch those back now. So I've got 2x equals pi over 6 and 2x equals 5 pi over 6. So now I can isolate x. It's a lot easier for me to isolate x here than it was when I had it with the sign before I put the little back box around there. Divide both sides by 2. I get x equals pi over 12 and x equals 5 pi over 12. I'm kind of getting crowded out there. But notice our domain. Our domain is 0 to 2 pi. We have more solutions now. The reason why we have more solutions, so let's take a pause on what we're doing here for a second. I'm going to go back up with you and just review what we've got. Here is the sine wave, one cycle of it. That's 2 pi right there. That's one cycle of the sine wave. But the question I'm doing right now, if you look right to here, this is what I'm solving. I don't have sine x. I have sine of 2x. That's really a horizontal compression by a factor of 2. So that means my wave is really actually looking like this. So in the domain of 0 to 2 pi, I can fit a whole other cycle in there. That should be going down as low as that one. I can fit a whole other cycle in there. Here's 1, and here's -1. So I've got my first few answers. I've got pi over 2. So let me just label this here. This space here, this is pi. This is 2 pi. There's pi over 2. And there's 3 pi over 2. I'm looking for when sine of 2x is equal to 1/2. So 1/2 is, let's say, here's 1/2. So I should have 1, 2, 3, 4 answers because there's 4 places where that wave has a y value or has a height of 1/2. There's 4 spots. I found 2 of them already. I found pi over 12. That's the first one. I found pi over 12. It's down here. I'm circling it down here in the bottom. And I found 5 pi over 12. So my graph's not great, right? This would be this little one right here, 5 pi over 12. So I found those 2. How am I going to get this value and this value? How am I going to find those 2 values? All I need to do is add on a period. I want to take this pi over 12 here, get my laser pointer. I want to take this answer, pi over 12, and I want to add a whole cycle onto it that will land it right here. So I take pi over 12, I add a period on. Now think about what a period is. And take pi over 12, I'm going to add a period on. That will give me my next answer. Then I'm going to take 5 pi over 12, and I'm going to add a full cycle onto that one. That will land me at this point here. So we have more solutions because what is our period? Let me work on that here. Our period is always 2 pi divided by k. in this case, our k value is a 2, so our period is pi. So I have to add pi on to both of those answers I circled in purple on the bottom. Sine of 2x is a compressed graph, so we have more solutions. That's why we have to add a period on each time. So I'm going to, well, I guess I'll keep it along the bottom here, but it is a bit crowded. My next answer for x is going to be pi over 12 plus pi, plus a period. So using the same, pi is the same as 12 pi over 12. So that gives me 13 pi over 12. That's my next answer. Then I have one more. So here's this one right here is my 13 pi over 12. Now my next one, my last one, I take my pi over 5 pi over 12. That was originally my second answer was 5 pi over 12. I have to add a cycle on there. I have to add pi on. And that's the same as 12 over 12. So my next answer is 17 pi over 12. And these are, that's this one right here. These are all less than 2 pi. 2 pi, if I use a denominator of 12, 2 pi with a denominator of 12 is actually 24 pi over 12. So I know I haven't gone over that with my 17. 17 pi over 12 looks like a big number, but it's within my domain. I'm going to write these all out kind of a little more tidily for you here. So your answer should look something like this. Therefore, x equals pi over 12, always in order, low to high, 5 pi over 12, 13 pi over 12, and 24 pi over 12. I'm going to erase all this stuff in the middle here because I need it to do my second example. So I'll press pause and copy down your notes because I'm about to erase it all. That's better. Part B. We have to solve for x. When is sine of x over 2 equal to cos of x over 2? What are the values of x that will make these two graphs or functions equal to each other? So again, we can't solve an equation when we have two different functions, or they're called arguments also. We have sine and cos. I want to use just sine or just cos, or it doesn't matter, but I need just one here. Now, what the strategy we're going to do here is we're going to divide both sides by cos, and the only reason we can do that, well, let me just do that first. Let's do the first step first here. I'm going to divide both sides by cos x over 2. So I'm going to divide this side by cos, we're dividing by itself, and this side by cos x over 2. These cancel out, of course, and they turn into a 1. Sine over cos is equal to tan. That's how I get away from two functions and get to 1. So what I have here is tan of x over 2. Now, you can only do this, what I just did divided by cos, because tan is sine over cos. That is what the tan function is. Normally, we cannot divide by a function because that introduces more restrictions that weren't necessarily there. And we're not talking about restrictions at all with this unit, but think of restrictions before when we did rationals. If we had 3 over x, okay, we've got restrictions on that. X cannot equal 0. If this weren't here, I wouldn't have any restrictions. So that's why we can't just divide by a function, because it introduces restrictions. This is a singular case because tan actually is sine over cos, so that's keeping the restriction there. Anyway, okay, let's go on. We've got tan of x over 2 equals 1. So if you don't like that x over 2, you can change it. You don't have to, but let's change it to, let's let x over 2 equal theta, if you want. We have tan of theta equals 1. Anytime you have a function that's equal to 1 or -1 or 0, it could be on the unit circle. Can you think of when we will get, so tan is opposite over hypotenuse? Sorry, opposite over adjacent. Adjacent. It's also y over x. Do we have a triangle that has an opposite of 1 and an adjacent of 1? We put an x and y axis here. An opposite of 1 and an adjacent of 1. So let's just draw a triangle in the first quadrant. The first quadrant's always positive anyway. If this is theta in the corner, I need an opposite of 1 and an adjacent of 1. Is there a triangle for that? For sure. That's a root 2. That's going to be my pi over 4. Pi over 4. Now, can I have a value of tan being positive 1 in any other quadrant? Cast rule. C-A-S-T. Where else is tan positive? Tan's positive down there in the third quadrant. So I pick up my triangle or my angle. I put it all the way down here. So here's the same theta. There's a -1 and a -1 and a root 2. And of course, -1 over -1 is positive 1. So what is this rotation? What's this one? Our first one is pi over 4. This one's pi over 4. What's our second one? All the way to the negative x-axis, that would be a pi. With the same denominator we're using as a 4, that would be 4 pi over 4. So for theta, I'm getting pi over 4 for one answer, and 5 pi over 4. Those are my two answers. However, we switched it. Remember, it's not theta, it's actually x over 2. So let's put it back. X over 2 is pi over 4. And x over 2 is 5 pi over 4. Solving for cross multiplying this 2 up, we get x equals 2 pi over 4, which is pi over 2. Multiplying this 2 up, we get x equals 10 pi over 4, which is 5 pi over 2 when we reduce it. So take a look at our domain. In the original question, the domain is 0 to 2 pi. What do you think? Well, look, let's do a reminder of our original, our x over 2 right here. That's actually a horizontal stretch, not a compression. So we've taken the tan function, we've stretched it. This term right here, this answer has been stretched outside of our domain. 5 pi over 2, our domain is from 0 to 2 pi. Sorry, x, not theta, x. And with these denominators, that is 4 pi over 2. 5 pi over 2 is outside of the domain because we had a horizontal stretch. So this one does not count. And that's because of our period. We had a horizontal stretch. So it pulled that last one outside of the domain. The previous question we did, it pushed everything back in. It squeezed all our answers back closer to the y-axis. This time it's pulling it out. And you can always check on Desmos to see what it will look like. But our only answer is this one. X is pi over 2. That's the only solution to this question. So speaking of Desmos, let's look at a question like that. Use the graph to solve the following equation. 3 tan, so the colors match here. This kind of burgundy color is this burgundy one here. 3 tan theta, and tan 2 theta is the light blue one here. And before we answer it, I'm just going to point out the expectation to you. You have to be able to solve linear and quadratic trigonometric equations with and without technology. So this is the with technology part. This is where you are given a graph, or you're allowed to use Desmos to create your own graph to find your answer. So when you're doing it on your own with technology, if you're using Desmos, you just click where they intersect and they'll put little kind of gray dots at the exact answers there for you. So when you take a look at this, you should be able to see where the burgundy graph and the blue graph intersect each other. And we're just going to go from 0 to 2 pi. So here's 2 pi here. So we're going to get all the values between 0 and 2 pi. Of course, there's an infinite number of answers here. But looking at the graph, you should be able to identify those answers. Those are all the points of intersection. So that's an example of how you solve it with technology. Of course, our focus is going to be without technology, because anybody can use Desmos to give them the answers, but that's not what we're looking for here. Okay, on to example 3. Solve for x in this domain. And luckily this time we just have one function. We've just got a cos. We don't have to worry about going back to all of our formula sheets and what can I switch this out with. I don't really need to because I just got cos. I am going to change it a little bit though. I'm going to let theta equal 2x just so I don't get confused. And sometimes what students do is they take this 2 here and they want to divide everything by 2 to get rid of it. You can't. It's part of the angle. You can't get rid of it. So to prevent that from happening, this is a good step here. You don't have to do that step, but sometimes it just saves you from making a mistake later. So let's sub that in there. That looks a little better. Now I'm going to isolate. Let's bring that root 2 over to the right hand side. Now we have a negative root 2. Now I can divide by 2. That's to get rid of this 2. I still have kind of the 2 inside the angle, but I'm not touching that right now. So divide both sides by 2, and we have this. This is about as simplified as we can get. Without a calculator, how can we find the value of theta? Without a calculator, of course. How am I going to find a triangle that has an adjacent of root 2 and a hypotenuse of 2? Hopefully some of you are recognizing this as somewhat familiar. We're going to unrationalize. So to unrationalize, I want to get the radical back in the denominator because that's what I'm used to seeing. It's the same process as rationalizing. Multiply both sides by root 2 over root 2, and the 2 root 2's in the numerator become a 2. Now these 2's here are going to cancel out. So 2 times root 2 is just 2 root 2. I'm going to cancel out those 2's, and I get negative 1 over root 2. Okay, now we can work with this. Remember that this is cos is the same as adjacent over hypotenuse or x over r. So I'm trying to find an angle. Let's draw a triangle here. Doesn't really matter what orientation you draw the triangle in. That should be a straight line there. Didn't do a very good job. Okay, that's not much better. There's theta. My adjacent is a 1. I'm going to ignore the negative for now. My hypotenuse or my radius is a root 2. What triangle is that? So this would be, the opposite side would also be a 1. This is a pi over 4 or a 45 degree, but our domain is radians, so we can't say 45 degrees. This is a pi over 4. Now I go back and think about this negative sign in the front. I know that cos of pi over 4 is 1 over root 2, but I need negative 1 over root 2. So now I have to think of my quadrants. So let's just put an x and y axis right here. So the one I've drawn is no good because I don't have a negative. Where is cos negative? Cos is negative in quadrants 2 and 3 because cos is x and our x values are all negative here, right? X, negative 1, negative 2, negative 3. These are all negative x values. So that's why I can, whoops. That's why I know it's in those two quadrants, because x is negative over there. So I take my angle, which is pi over 4. I put it in quadrant 2. There's pi over 4 there in quadrant 2. Now what's this rotation? What would that rotation be? That would be 3 pi over 4. So I've got theta. My first one I got is theta is 3 pi over 4. And now I take my pi over 4 quadrant and pi over 4 angle and I put it in quadrant 3. There's my pi over 4 angle there. And what's this rotation? That one is going to be 5 pi over 4. But now we go back to our original exchange that we made here. And we're going to put that all back in. So let me, maybe I'll move over to this. Well, no, I can fit it here. Back to a 2x. 2x equals 3 pi over 4. That was 1. And 2x equals 5 pi over 4. Divide both sides by 2. 3 pi over 8. 5 pi over 8. Since we have changed the denominator, we can now get more answers. So we have to think about our period again. 2 pi, our period is 0 is less than or equal to x, which is less than or equal to 2 pi. Now 2 pi, look at the denominator, is the same as what over 8? It's 16 over 8. So I can certainly get some more answers here. This is again an example where I've taken my cos wave and I've compressed it. I've compressed it horizontally. So what's happened is I've taken those two answers. Let me draw a cos wave for you here. So here's one period of the cos wave. That goes to 2 pi. Halfway here is pi. Now I have compressed it horizontally, so I can actually fit 2 in the same horizontal distance. So let me try and squeeze. There's 1 and there's 2. So now I've got 2 cos waves in the same domain. So my original answer that I got here, 3 pi over 4. 3 pi over 4 is, let's say, about here. 3 pi over 4 is there. This point here has been pushed right over, and now it's here. It's at 3 pi over 8. So to find its other matching one here, I need to add on a period. Add a period onto both of my answers. We'll go back down here. I've got to take, so I'm going to, and I've got these answers here. X is equal to 3 pi over 8 plus a period. That's 8 pi over 8 because a period is pi. That's going to give me 11 pi over 8. Can I add another period on and get another one? Well, if I added another period on, if I take 11 pi over 8 and I add on another period, that's 19 pi over 8, and that's outside of my domain. Remember, I can only go to 16 pi over 8. I've got 2 waves in this domain, not 3, so I can't keep adding on another period. And I've got this one here, x equals 5 pi over 8. Let's add on another period. That will give us 13 pi over 8. So we can't keep adding on another cycle because it's too big, but because we did change our original question from theta to 2x, we had to put it back in, and that was a horizontal compression. So we got more answers. Let's make a nice clean answer here so that when I'm marking your work, I don't have to look through the mess like I've put here. I can find your answer. Therefore, x equals, and we put them order low to high, 3 pi over 8, 5 pi over 8, 11 pi over 8, and 13 pi over 8. There's all of our solutions for this question. If you still don't have those triangles memorized there, you need to do that. Otherwise, you're unable to draw these diagrams all the time. You're unable maybe even to find the proper quadrants. So you have to memorize those special triangles. Since evaluation of this chapter does not allow calculators, if you come across any questions in your homework that say answer to 1 decimal place or using a calculator, they're still good practice, but you can skip them and focus on these questions here. Still, those questions aren't that comprehensive. In addition to those ones, I want you to try these ones here. These, I've got some hints there for you. And the last slide here are the answers to those questions when you're ready to do them. So work hard and message me if you have any questions.